Auzubillahiminash-shaytanir-rajim. Bismillahirrahmanirrahim. Class 10th, Subject Physics, Unit number 10, Simple Harmonic Motion and Waves. Today we will discuss about the simple harmonic motion. Today's our topic is simple harmonic motion and it is can be written like this: SHM, simple harmonic motion. First of all, a body is said to be vibrating if it moves back and forth or to and fro about a point. Another term for vibration is oscillation. A special kind of a vibration, vibratory or oscillatory motion is called the simple harmonic motion, which is the main thing. Okay, in daily life we observe a many type of motions. Some are vibratory, rotatory, linear motion, and so on. There are lots of types of motion, but we will discuss here about the simple harmonic motion. First of all, I will tell you about the proper definition of a simple harmonic motion. And the simple harmonic motion definition is that a simple harmonic motion is a to and fro oscillatory motion in which acceleration of the body is directly proportional to the displacement of the body from the mean position and is always directed towards the mean position. In this definition, we discuss that the acceleration of the body is directly proportional to the displacement, and and it is always directed towards its mean position. So here is the definition, and I will explain this definition by the motion of a mass attached to a spring. Here first there is a definition. So here is a definition. Simple harmonic motion is a to and fro oscillatory motion in which acceleration of the body is directly proportional to the displacement of the body from the mean position and is always directed towards the mean position. So for the explanation, I am using a simple example and most common example, that is a motion of a mass attached to a spring. Here is the motion of a mass attached to a horizontal spring. In the first figure, we can see that there is a spring and attached with a mass m, and at this position is it's a mean position here, and here is the extreme position A and extreme position B. There is a displacement from these extreme position and it is denoted by x. If this spring is stretched or compressed to a small displacement x from its mean position, it exerts a force on the mass like this. Here it is in the rest form, and when we stretch a spring and take a small displacement like this, it will become on the extreme position A, and we exerted a force here. According to Hooke's law, the force is directly proportional to change in length of the spring. And here I have a relation, and here is a relation: force is directly proportional to displacement, and this negative sign shows that means that the force exerted by the spring is always directed opposite to the displacement of the mass. So because the spring always exerts towards the mean position. Clear? Okay, now where x is the displacement of the mass from the mean position O, and k, here k is the relation. Here f is equal to k minus x. Proportionality sign is replaced by the constant k, and k is called the spring constant. Okay, here again I'm telling you about, let's suppose we stretch a spring in that form and it comes on to the extreme position A. That's why the force exerted on a mass m, and it is stretched and it goes to the extreme position A. Now we can say that how much we force applied on a mass, the spring displays from the distance. The force and the displacement is directly proportional to each other. So the relation can be written in the form the force is directly proportional to the displacement. Okay. Okay, now by Hooke's law, this is the relation that force is exerted on a mass is directly proportional to the displacement. For a proportionality sign, we will replace it by a constant, some constant, and we use k constant. Clear? Here, k is the proportionality constant, and other word you can say that spring constant. Spring constant. If we want to find the constant value of the spring, then it can be found. Here minus x is multiplicative with k. When we take it to another side, it will be a dividend. So we can find the value of here k, and that is the called a spring constant. Okay, now according to this, the value of k is depends upon the stiffness of the spring, and stiff springs have a large value of k and soft spring have a small value of k. Okay, now as we know that about the we have read that according to second law of motion, we know that the force is equal to mass into acceleration. Mass into acceleration. Here we have to put the value of this f into the relation that we have find in the first one. Here by putting values, we know that f is equal to k minus x. Here f value is mass into acceleration, and here k minus x. According to definition, we have discussed that the acceleration is directly proportional to the displacement. Okay, here we have to find acceleration. Mass is multiplied with, and when we take to another side, it will be a in the dividend form. So k over m into minus x. Here it means that the acceleration of a mass attached to a spring is directly proportional to its displacement from its mean position. Here we can say that the both values k and mass is constant. Suppose k over m constant, and we put k over m is equal to 1. Clear? Now the relation we will find minus x. Here this is the definition that the acceleration of a mass attached to a spring is directly proportional to its displacement from the mean position. Hence, the horizontal motion of a mass spring system is an example of a simple harmonic motion. Here, the negative sign shows that means that the force exerted by the spring is always directed opposite to the displacement of the mass, because the spring force always act towards the mean position. It is sometimes called the restoring force. Sometimes it's called the restoring force. Okay, the restoring force. A restoring force is always pushes or pulls the object performing oscillatory motion towards the mean position, and this is the definition. Okay, definition is that a restoring force always, yes, here is a restoring force. A restoring force always pushes or pulls the object performing oscillatory motion towards its the mean position, and that is called a restoring force. Here we will see that here. Now we can see that in the figure that when a spring is stretched, then it then when a spring is attached, it goes to on the position initial position A. Now here in the figure the object is not stretched, it is on the rest position at x is equal to 0. You can say that that is a main position. Initially the mass is at the rest in the main position O, and the restoring force on the mass is 0. Here we can see that no force is exerted, so F is equal to 0. Suppose the mass is pulled through a distance x up to extreme position A and released here when we release it. Or you can see that other figure that we have discussed before. I can show you. Here you can see that the first figure in this, there is no force is exerted on a mass m, so it is on in the rest position. So when we stretch a spring to extreme position you can say that, in other words, we applied a force on a mass m and stretch to the extreme position A, then it comes on extreme position A. So when we release it, the restoring force exerted by the spring on the mass will pull it towards the mean position O. Due to the restoring force, the mass moves back towards the mean position O. The magnitude of the restoring force decreases with the distance from the mean position and becomes 0 at O. Here, another figure, I will explain it. Here you can see when we apply a force on it and it take it to the extreme position A, and we will release it by the restoring force of the spring, it will become goes on to the extreme position A. Due to inertia, it does not stop itself in the mean position, it goes towards the B. Here you can see that the distance from the O to A is positive A, and so the direction is opposite, so that's why it become negative at the position O to B. Here you can see that however the mass gains speed as it moves towards the mean position O, and its speed become maximum at O. Due to inertia, the mass does not stop the mean position O but continues its motion and reach the extreme position B. Here we have discussion that at the extreme position A, the kinetic energy will be 0 because the kinetic energy is the energy that is due to the motion, and the potential energy is the energy that is due to some a reference point or some position. So here it is its extreme position, so here the potential energy will be a maximum and kinetic energy is a 0. So when we release and it becomes on a O, extreme position O, here the body does not stop itself, it continues its motion. So that's why due to motion the energy is known as a kinetic energy, and it becomes maximum and potential energy 0. And similarly when it comes to the extreme position B, here kinetic energy will be 0 because it stop itself for a while. So that's why its all kinetic energy will be 0 and its potential energy will be maximum. So as the mass moves from the mean position O to the extreme position B, position steadily increases in the strength. Hence, the speed of the mass decreases as its move towards the extreme position B. The mass finally comes briefly at rest at the extreme position B. Ultimately, the mass returns to the main position due to the restoring force. So this process is repeated and the mass continues to oscillate back and forth the mean position O. Such a motion attached to a spring on a horizontal frictionless surface is known as a simple harmonic motion. So by this we can find the time period of a this object, and for the time period we know that the time period t of the simple harmonic motion of a mass attached to a spring is given by the following equation, and the equation is here. T is equal to 2 pi m over k. Here this is the formula by which we can find the time period, and time period is known as a the time, the short interval of the time of an object in which a object complete its one complete circle is known as the time period. And here is the topic.